I tried two rate limiters using Python and Golang and load tested them to see which one performs better. Hey friends, welcome to the channel, and if you're new here, my name is Kaushik and I make videos about system design but with a slight twist. Each week, we go through various practical concepts and try to build out components to see how they interact with each other instead of just whiteboarding a few ideas. So if you like the idea of this channel, stick around and I'll tell you a lot more about how these components work together. In the last video, we used Python and Flask to build a basic rate limiter. In order to store the context of the various tokens for the users, we also leveraged the power of Redis. But if you think about it, it was a very simple rate limiter to just help us understand the concept of token bucket algorithm. It was not very scalable, it was not very practical, and it certainly cannot handle large loads. So in this video, we are taking things slightly further. We will be using Python Fast API, which is Python's answer to async programming. Fast API supports async natively, and this means that even if we have any amount of latency on the Redis side of things, the server should still be able to process requests and the users should not feel much bottleneck or much sluggishness in the application. But hey, it's still Python, right? There's only so much speed and optimization that you can get. So I decided to take things a little bit further. And that's when Golang comes in. Golang, as you all know, is a high performance compiled language and it has concurrency built in. For this particular scenario, I'm using Golang's internal rate limiting package and not leveraging any other tools like Redis. So as you can see, the con here is that it's not distributed. The pro here is that it's very simple and there are no dependencies. But if you ask me, would I use this in production? The answer is no. But we don't really care about that right now. We just want to see how all the components, when put together, react. And then we will also be doing a load test to see how they compare against various amounts of load. In this scenario, we are using Python and Fast API to build our rate limiter. And as I described before, Fast API is inherently async. We are using Redis like before to store our tokens. So if we quickly walk through the code here, you can see that this is the app variable that is initializing your Fast API server. Some config variables like Redis host, refill rate, bucket capacity, etc. You can inject that as part of your environment variable or as part of your CI/CD setup. However you have it, it should be able to pick it up using this get environment function. Initializing Redis here, default port and the environment variable. This is actually the calculate tokens function that we saw last time as well. It calculates the total amount of tokens for a given user, and it does that depending on how much time has elapsed between the last request and then also taking a minimum of the burst capacity and adding up the current tokens and the total tokens to refill. This is the get method actually that gets your data from Redis. We are simulating a small delay here, which is actually how it will be in your real distributed system scenario. Every time you make a call from your container or your service to Redis, there's going to be a small latency added. But since we are orchestrating this in our local, I have added this a small delay here. I've just commented it out for now. And the next one, if you see, is the rate limiter function, which takes in the Fast API request object. We have an X API key as a header that is defined for user. You can define this as a custom value as part of your larger application logic. This would make sure that you don't have to depend on the IP address of the user, which may or may not be similar. They can be calling your application from different places. They can apply some sort of an IP masking or IP change logic. This might sort of break your rate limiter. So it is very beneficial to have an API key dedicated to a user, which you can use to apply rate limiting. Then what we are doing is using that we are actually getting the value and calculating the tokens, and if the number of tokens is less than 1, we throw 429. Here we are then setting the new amount of tokens. So here we are decrementing the tokens, and one thing to note here is that we are using pipeline. Strictly, if you think about it, we don't need pipeline because there's only one set call. So what does it do? What does it do is actually batch all your Redis requests. So if there are multiple set calls that you are making to Redis, instead of making multiple round trips, it only makes one round trip, and that happens when your execute function is called. And then finally, a small API that or an endpoint that brings it all together. We are using the depends functionality in Fast API. That Fast API will call your rate limiter when this API gets called, and then we just return a JSON message. If you talk about the advantages of this or the benefits of this, you can say that this is highly scalable. It's async, it's not blocking. So every time you are waiting on a response from Redis, it's still unblocking because Fast API is async and the other user should be able to call you. And if you think about the disadvantages of it, it has a dependency on Redis. So every time your load increases, you will also make sure that you are evicting keys from Redis. You also have to implement some sort of a clustering in Redis as well. In this section, we are using Golang and its in-memory rate limiter. So as I mentioned, there aren't any external dependencies like Redis or any other cache or token maintenance mechanism. So if we quickly walk through the code here, you can see that we have imported the time/rate package from Golang. This is sort of a class and a constructor construct. If you're from the Java world, you will be familiar with that. So we are creating a class or a struct in the case of Golang, which holds a reference to the limiters and a mutex lock, which we'll see in a second. And then this is the sort of a constructor function or a new function, new object initializing function that gets called when the Gin server is up and running. And then this is the get rate limiter that actually initializes rate limiter for each of the user, and it actually creates a new instance of the map that contains the rate limiter. If you see, we have a read lock here before we read the map from the limiter. So what this actually does is that it allows concurrent access for Go routines without blocking the thread, or it allows other Go routines to also read at the same time. But the only condition is they should not be writing. So this is only a read lock, and it's very efficient and it's very good for fast lookups. So if that does not exist, which means it's the first time the user is accessing our application, so we create a new limiter. We initialize that with a burst capacity of 10 and a refill rate of 5 per second. So as you can see, we don't have to write any amount of custom code or any new function to define a rate limiter. Go has an idiomatic way of defining it in the language itself, which is very handy. So all you require is one line of code as opposed to having like 3 or 4 lines and maintaining 4 or 5 variables. That's pretty good. And we have a write lock here. So once we have initialized the rate limiter, we are now assigning it or putting it inside the map. And since this is a write operation, we want to make sure that it's synchronized and other Go routines are sort of not messing with it. So that's why we have a mutex write lock. If you look at the rate limiter middleware here, so this is getting injected in the request response lifecycle for Go and Gin. And this takes in the API key limiter reference, and it returns a handler function, which is the way in which we can define rate limiting capabilities or any middleware injection for Gin. We get the header from the API key header. Like we saw early on, it's a custom way to define a header for user. We do not have to depend on IP. If that header is missing, we throw a 403, or I think it's a 401 unauthorized. We abort that and we go back. If not, if the key is valid, again, we are not essentially checking if the key is valid or not. That's depending on the authorization or authentication service that you can take care of it separately. We get the rate limiter, and then if we check this is allow or not. So this is basically us trying to see if the amount of tokens is greater than 1. So if that is the case, or if that is not the case, then we just abort and send 429. And what this also internally does is that it decrements the token by 1, so that we don't again have to carry out that operation by ourselves. And then it just passes on the controller to the next middleware. So people coming from the Node.js Express background would be familiar with this. The way we inject middleware is somewhere here. So we use, so this is a different middleware for logging and recovery. And here we are doing the rate limiting middleware. If you think about the pros of this approach, it's very fast, very scalable, and does not have any external dependencies. Actually, it's not that scalable because the more users are there, the more the size of the application will increase in terms of RAM. So it's not that scalable, which is a con. Let us now load test these two applications. I have used K6 for this, and it is a very good load testing application for developers and SREs. You can download K6 for any operating system of your choice, and you can write tests in pure JavaScript. It's also built by Grafana Labs, so it has very good visualization tools and you should be able to visualize a lot of metrics in a very good fashion. I have three scenarios in which I'm going to test these applications. Number one is running all these applications directly on my Mac, no containerization, no constraints whatsoever. Number two, orchestrating them using Docker Compose. So both the applications are running inside a Docker container. The Redis is also running inside a Docker container, but we have no constraints imposed in terms of RAM or CPU. And number three is very similar to number two. We have 1 GB of memory and only one CPU, and we are running this on Docker containers. And the Redis is also having a memory constraint of 512 MB of RAM and 0.5 CPU. Let us now look at the results. So in the first scenario, where we do not have any constraints and we are running on the Docker containers, if you look at the total request duration, you can see that the P95 latency is 32 milliseconds and the P99 was 98 or 100 milliseconds, which is slightly slower. You can check the throughput here, which is 446.08 requests per second. Again, remember, we do not have any constraint, and this is the Python version of the rate limiter. If you look at Golang, it's quite faster as expected because it is compile time and highly concurrent, and it also has the in-memory rate limiter as opposed to the Redis rate limiter. So if you see the P95 latency, which is 20 milliseconds, and P99 is 30 milliseconds, and the throughput is also slightly better. It's 454.73 requests per second. Second, let's look at the Docker containers, but with a constraint of 1 GB of memory and one CPU. So here, if you see the request duration values for P95, 21 milliseconds and 80 milliseconds, which is fairly similar. The throughput is also 452.66. Golang, again, similar, better than Python, but not as good as the previous one where we did not have any constraints on Docker, right? So P99 is 51 milliseconds, P95 is 22 milliseconds, and then the throughput is 453. But when we go into the bare metal and the first scenario that we discussed at the start, that's when things get a bit interesting. Python, as you can see, performs fairly similar. It's slightly faster than the previous two versions, 28 milliseconds P95 and 47 milliseconds P99. Throughput is 455, but check out Go's performance. Go's performance, when directly run on my Mac, was blazingly fast. It was 3 milliseconds for P95 and 6 milliseconds for P99, and the throughput was also quite higher, which was 490.42 seconds. So there you have it. Go was blazingly fast under most circumstances, even inside Docker containers and even on bare metal systems. But I ran quite a few iterations under the CPU and RAM constraints, and in some instances Golang was slightly slower. And I think this is mostly because of two things. The first is that it's actually an in-memory rate limiter, so it's constrained on RAM. So as we were bombarding it with a lot of requests, the RAM was growing, but there was a constraint, and hence the throughput and the latency got affected. And the second was also, because we placed some mutex locks, there was a lot of high contention, and when we had a lot of requests, the read writes were slightly slower. Now this wasn't the problem with fast API because we had offloaded this read and write to Redis, but in our case in Golang, it was still inside the in-memory. So we saw two rate limiters using two technologies, and one was using Redis to manage the tokens, and the other one was just in memory. We also compared the pros and cons of both these approaches, and we also visualized the performance, saw various latency and throughput metrics under varying loads. I have added the code to GitHub, and I encourage you to try it on your own under the same scenarios or different scenarios, and definitely share your results with me. If you want to watch more of these videos, please like and subscribe. It would greatly help the channel. And if you want to watch my other video about building a simple rate limiter using Flask, you can check it out here. Thank you so much and see you in the next one.